So some of you are wondering about progress on the Steampunk receiver. As I look inside and take it apart further, I see that it really is going to have to be rewired. There's some flying parts and really poor solder connections in here. So we're going to have to take this thing apart and rewire it. Playing with a simple plug-in coil regen, what can you apply from that circuit into the early 30s Steampunk regen, and without going crazy, try to improve its performance? So I actually have some cloth-covered wire on order, so I can do some repairs in here and feel good about it. We know the choke needs to be removed because it's open circuit. It'll be interesting to see what this choke's all about anyway. Oh, okay. There you go. That is really an interesting choke. Maybe it's repairable even. But in any case, I can certainly slip a choke inside this package and it will look right on the outside. Okay, side number 2 is off, and this really had to be done. You can see the horrible soldering and the terrible wiring that's in here. It really is going to need a rewiring job, so we'll correct the mistakes. It's easier to get at things now with this side panel off. So I was able to get the innards out of the choke, and now I have the plastic case and the bottom piece. There's no continuity, so I can't tell you how many millihenries this is, but it's probably a lot. It's probably at least 10 or 15 millihenries. Really overkill for a regen. I want to be able to stuff a choke inside this container. If you look at those $20 chokes that you can get online now, they're too big anyway to fit in there. Perhaps some of the smaller ones that you can get, you know, the 1 millihenry, 2 millihenry chokes would fit in there no problem. But I did happen to have this really beat up choke. This guy is in pretty sad shape, but it has continuity. So I think I can doctor this thing up, maybe give it a good coating of polyurethane, get some wires on the end of it, and I believe that will fit inside this case. And that's going to be the choke I'm using. So I'm using one that I don't want to show off. It's really in bad shape, but it still is a choke, and that's going to go inside. I'll seal that up, and that'll be the choke for the Steampunk regen. Okay, the radio frequency choke has been put into the old choke package that held this beautiful coil type choke. And the Pi multi-winding 2.5 millihenry choke is really a better choice for shortwave and down through the broadcast band. So the next step is simply to glue on this cover, and this choke will be ready to go into the receiver. Radio frequency chokes were available at this time, that's for sure. This is a 1933 Allied catalog, and you know, they list radio frequency chokes. Here's 2.5 millihenries for use up to 550 meters. So that's, you know, that'll cover the broadcast band. And it's good to look at a lot of other components. You know, when you look through here, you say, oh, was this particular style of capacitor used at that time? And you can see that many of the capacitors that are used here are commonly available by the early 30s. So it's no trouble finding parts. I have a lot of antique parts that'll fit very fine in this receiver if I need to replace anything. So this one tube receiver schematic and project was published way back in the mid-1930s by W6AJF Frank Jones in his West Coast Handbook series. It uses the brand new Type 19 dual triode, which debuted in about 1933. I'm using this as an example of a good two-triode design from the era, and we can use Frank's ideas to our advantage in the Scotty Regen rebuild. Jones included the plug-in coil data, but you must be mindful of the variable capacitors that he chose, which turns out to be pretty similar to our set. You can see that Frank is suggesting a 140 picofarad throttle capacitor in this excellent circuit. He also goes for extreme light coupling to the antenna. Rather than using a trimmer cap, he's using a gimmick, which is just twisted wire on the antenna lead-in. So he hooks up the 3-volt supply, which lights up the tube, in such a way that the negative lead also does double duty to bias the audio stage. This is very clever, and it eliminates the C battery altogether. So you just have a 3-volt cell and a 45 to 90 volt B battery. Now, whether we actually use this idea or not, I think I'm going to stick with the separate C battery just for clarity, and kind of as a wink to the original author who understood A, B, and C batteries. So if we go on to Frank's coil winding guide, because his capacitors are similar to ours, I think these are a really good guideline for the coils, and I'd like to compare these to the coils that the builder actually made himself on the tube bases. Now, of course, it'll be a little bit different because tube bases are a lot tighter than a full-size plug-in coil. Let's look at the original schematic as I attempted to draw it. And it's basically a working circuit, but I believe that the lack of good grounding on the filaments is causing coupling, direct coupling between the two stages. Maybe he got away with this because primarily in the early 30s it was all CW communications. So once this thing is regenerating in an autodyne fashion, it's fairly stable. But it sure would have been difficult to deal with AM stations. He's using 150 picofarad fixed capacitor as his regeneration kind of level set, and then doing the rest with this potentiometer, which of course in series it's going to change the voltage on the plate and affect the regeneration level. The regulation on such a system as this had to be pretty poor. Now, if we did ground this point right here and turn this into a voltage divider, you'd want the wiper to go up to the transformer. The problem with that is now you start to draw current from your B battery through the potentiometer. So really, he at least knew to not do that, and that prevents B battery voltage from being run down continuously. Here's what I decided to do on the rewire. First of all, I got rid of that radio frequency choke, which I kind of believe that was in there to try to fight this feedback problem he had between the two tubes. It would allow the DC and the audio to pass okay, but it would block any RF from this stage getting back into the regen stage. The radio frequency choke is now 2.5 millihenries and not the higher value that I assume that choke was originally. You can see both tubes are now in parallel, and they're being powered off the A battery through the rheostat, and I've hooked that up with the center attached to the other side. So this is what I'm going to build. Notice that everything is well grounded. Everything should go to a solid ground. I don't like lifting up grounds, except maybe in center taps for like power supplies or for keying stages with a key. You don't want to be floating grounds. You want your grounds to go solidly to chassis all over the circuit. Now, if we did want to put the potentiometer in the proper way so that the wiper is supplying power to the regen and this becomes a voltage divider, we would send one side to the plus and one side to ground, and we would have to use a double pole single throw switch to kill both the A voltage and the B voltage just for safety. But again, I think adding such a switch takes away from the original design. In the next video, I will be deep into the rewiring. I've obtained appropriate cloth covered wire for the cleanup, but I didn't want to leave this video until I showed you the plug-in coils for the set and the approach that was taken by the ham way back in the 30s. So of course your regen won't work. But why? Why won't it work? That's the question. Now, of course, the The thing we're trying to do is we're trying to get some feedback, some positive feedback between the tickler coil and the main coil. We'd like these two to be in phase and at a high enough level that we can get oscillation, at least to be tempted. The problem is the darn tube inverts the signal. So instead of producing positive feedback, it produces negative feedback. And basically this won't oscillate, so you end up fooling around with the thing until you get frustrated, and finally you swap the tickler coil and you say, hey, it works now. And this has to do with the way that we draw the circuit. We take it literally in the schematic form. That is, we build it on the plug-in coil or on our cardboard toilet paper tube just the way it is on the diagram, and it won't work that way. So, for instance, this guy isn't going to work because you just wound the coil exactly like it shows in the diagram, where these two absolutely need to be swapped. Here's somebody that actually had the problem and drew it correctly to reinforce that you've got to flip the tickler in order to get it in phase. This guy won't work. This guy, he got it. See, he flipped it so that you can see that it's going to be in phase. This looks right. This looks right. This looks right. Oh, Mr. Jones, this looks right. Oh, this guy's really fancy. Look, he put the dots on there. Of course, he's forcing the idea that you have to have these actually in phase. This guy gets a gold star. Nope, not going to work. Not going to work. Sorry, Mr. Morgan. Not going to work. No good. Not going to work. Not going to work. Oh, this guy's terrible. This is not going to work. Nope. No, Mr. Kitchen, I'm sorry. This isn't going to work. Not going to work on the twinplex either. Nope. Oh, here's somebody that caught up. Very good. This will work. Not going to work. Okay, you get the idea. You guys are probably pissed off by now, but I just wanted to tell you that if you take these schematics literally, you still have to make sure that you've got the two coils phased correctly. So to finish off this video, let's talk a little bit about plug-in coils. So what plug-in coils give you is band switching capability. Now, of course, you can do this with a special rotary switch or something like that, where you can change bands and have fixed coils for all of the bands and have it all on one knob on the front of the receiver, but that makes for a pretty complicated setup. And it also messes up your RF design sometimes and your performance. Plug-in coils allow you to separate stages easier when you're building super heterodynes and tuned radio frequency type equipment. But for a regen, it's just a handy way to change bands, and it gives you more flexibility. The problem is your regen has to be able to support all of the bands that you're intending to use. So if you're designing a set, for instance, for the broadcast band or for long wave, it probably won't work as well as a shortwave receiver. First of all, your tuning capacitors are going to be so large to cover the broadcast band that if you're trying to tune upwards of 40 meters and 20 meters, the band becomes just a little fraction of a degree on the dial and makes it tough. Fortunately, our Steampunk Scotty Regen is specifically designed for the ham bands, shortwave frequencies, and both its band set capacitor and its band spreading capacitor are both low values. I estimate that the band spread main tuning is probably around a 25 picofarad variable, and the band set capacitor looks like it can't be any more than 50 or 60 picofarads. This would never do for the broadcast band, that's for sure. But for the ham bands, it's a really good choice. So here's some of the common plug-in coils that have been available throughout the ages. We have these very small 4-pin jobs. These became very popular in the 40s. The larger or standard size 4-pin phenolic forms came out, and these were used for most of the regens in the 30s and 40s. And these larger Hammerland forms, allow you to do broadcast band very easily. Notice this 80-meter coil is very similar to the 80-meter coil that we have in the set. You can see that it's almost perfect. This is a little more diameter, so there's fewer turns, and it works out pretty well. So the other thing that people did is they used tube bases to do the windings. This is a 20-meter coil here, and here's a similar coil done. Looks like there's a paper tube that's been glued onto the tube base, to make a homemade type plug-in coil. Also, these ceramic bases were available at one time. You could simply glue a paper or plastic tube to that and end up with a plug-in coil. These coils here, and these are fairly rare. This plastic melts quite easily too. These were very popular for sets like the Ocean Hopper and Night Kits, that kind of thing. These are 5 pins. Interestingly enough, with a 4-pin, you're only able to do a tickler winding and a main tuning winding, sometimes called the secondary winding. However, if you were to use a Hartley style regen, you can actually put 3 windings on a 4-pin plug-in coil, and you do that by using one of the pins as a common ground for all 3 windings. You can do that with a Hartley style. You can't really do that with Armstrong. With Armstrong, you need at least 5 pins to do 3 windings. Okay, so that's the minimum amount of pins to do a primary, a secondary, and a tickler is 5 pins. Now, if you're lucky enough to have 6 pins, that gives you even more flexibility. And of course, the ultimate in flexibility is the octal plug-in coil. It's got 8 pins to work with. This coil actually comes out of the famous Alenco solid-state shortwave receiver sold by Sears. I had one of these when I was a kid, and it required an oscillator and an antenna coil. So let's see what the guy actually built in the Steampunk receiver. It looks like there's an 80, this is an 80, and this is an 80. So he was having problems getting 80 to work. Looks like he made 3 coils. And it'll be interesting to see if any or all of these work. Here's the 40-meter coil. Notice with the 40-meter coil, he didn't have to put the tickler inside with a separate form. He's managed to put the tickler and the main tuning on the same tube socket. Boy, that's some clever winding right there. And then for 20 meters, of course, it's even smaller. You have the main tuning, which is this gapped winding down below, and the tickler is the close wind up top. Very common for the tickler to be close wound, and for the main tuning capacitor to have spacing. Basically, this gives you the best Q. The main tuning coil, the tickler. This is standard for a high Q coil. This coil says it goes from 5 to 10 megahertz, giving a high performance by the spacing of the turns, getting good Q on the coil. These are just things to keep in your back pocket when you're winding coils. So on the 80, he's got the tickler coil inside, and then he's gooped it with something. So these things are solid, and they're heavy. So one has to wonder what this stuff is. Maybe it's something that, some resin that was used in the automotive industry or something you could get at the hardware store. They're all filled with different kinds of goop. There's a lot of work that went into that. The tickler coil, again, is inside. The main tuning coil, or the secondary, is on the outside. So there we go. There's our rundown on plug-in coils. Can plug-in coils have the same performance of a good fixed an air ducts or a ceramic style coil? Probably not, but they come very close. Also, the old-fashioned type of vari-coupler type of arrangement, where the vari-coupler has the tickler coil and the fixed secondary coil, and then your coupling to the antenna could be another vari-coupler off the other end of the coil, or perhaps a smaller winding at the bottom of the coil. Generally, when you're building coils that have all three windings, you put the input coupling coil at the bottom, you put the main tuning coil in the middle, and you put the tickler coil on top. The coupling coil and the tickler coil are always opposite of the coil form. And you always go ground, hot, ground, hot. The tickler, of course, doesn't matter. You just have to make sure it's in the right orientation to promote positive feedback. So you'll end up switching the leads no matter what you do, just due to Murphy's Law.
I've got a few tips for building plug-in coils for regenerative receivers. And of course, the ultimate is a 3-coil system. The tickler coil, the grid or the secondary coil, and of course the antenna coil, which is the primary. When you see exact dimensions for building plug-in coils, those have to be taken into consideration of the circuit you're using, the exact variable capacitors. Everything has to be as the designer wanted you to do it. I've never been successful in saying, here's how you build a plug-in coil for a certain band, and here's how big the tickler coil needs to be, and here's how big the antenna coil needs to be. Usually there's some trial and error, there's some cut and try, and it has to do with how much gain the tube has or the transistor has. You may have to add or subtract turns on the tickler coil. You may have to add or subtract turns on the primary coil, because depending on the antenna you use, depending on the area that you live in, you may have to cut back the number of turns on the antenna coil pretty drastically. So when I see, instructions on how to do coils, sometimes you have to take that with a grain of salt. So a good example is the broadcast coil. I mean, you have an AM table radio and it can tune the entire broadcast band. Why can't I do that with my Regen? That's mostly because the coil and the variable capacitor are only capable of a certain range that's based on the way the coil's built. These plug-in coils have capacitance between the turns, and this, along with the variable capacitor, limits you. So most of the Regen circuits have 2 coils to cover the broadcast band. One called the high coil. The high coil typically will tune from 800 or 900 kilohertz up to 1.5 to 2 megahertz. And then they have a low broadcast coil that takes you down as low as 550 kilohertz. Some of them even take you down to 400 kilohertz to cover part of the LF band. Now, when you go to the higher frequencies, it does pay off to space your turns and to use thicker wire. So, for instance, this 40-meter coil, you could have 20 turns spaced of, say, number 16 or number 18 or number 20 wire. Or you could have 12 turns close wound of number 22, and they would both tune about the same band. But the one that has the spacing and the heavier wire is going to have higher Q, and you'll have better performance. In general, I like to put the tickler coil on top, the secondary or the grid coil in the middle, and the antenna coil on the bottom. The only exception to this would be if you have the tickler coil on the bottom and the grid coil in the middle. You might want to have a swinging link or a variometer in the top. Now, having a variometer in a plug-in coil doesn't make any sense, but perhaps a lift link could be in place. You place the plug-in coil into the socket, and then you swing the link over, coupling. I think I would prefer to have the tickler as the fixed coil in that case, and the antenna coupling up here as the swinging link. Anyway, just a few ideas on plug-in coils, and generally you're going to have a 5, 6, 7, or 8 pin to do 3 coils with an Armstrong type regen. The simple regen that we're working with only needs 4 pins. It has a tickler and it has a grid or a secondary coil. That's it. We loosely couple into the grid, and that's all there is to it. Is that going to have the same performance of having a primary? No, it probably will not work as well, but that's what we're stuck with the Scotty Regen.